Logistic regression, everybody's favorite. Okay, logistic regression is a subset of multiple regression. What it's going to try to do is find out which of the predictors are significantly able to predict the DV. And in this case, the DV, there's only two possible outcomes. They're both categorical. It's a dichotomous categorical outcome with only two outcomes. In other words, was the subject married or not? Will the subject survive or not? Pass or fail? Left or right? That kind of thing. So that's the big difference between a regular multiple regression and a logistic multiple regression is the DV is a dichotomous categorical outcome variable with only two possible outcomes. So what we're going to try to do is try to predict whether a person will be married or not based on their gender, which is a categorical variable, and a person's age, which is a continuous variable. Okay, so we're going to go ahead and build the model. Assumptions for logistic regressions, but again, we're not going to check them out in this video. So we're going to go to Analyze, Regression, Binary Logistics. Remember, our DV is our married, right? We're trying to predict if they're married or not based on their age and gender, so we're going to put that in there. Now with logistic regression, the predictor variables, your IVs, are called covariates. So we're going to put them both in there. And from the reading that we all read there was we should let the computer decide, and we're going to use a stepwise regression model, and we're going to use the forward. So that means it's going to use, the computer's going to pick the largest predictor for us, and we should also check for interaction. We got to highlight both of these and then hit this little interaction key, put them over there. So we're going to go to categorical. So this part is used to, this is actually the dummy coding part. We go ahead and kick in the categorical variable, and then we're going to set the reference category. Okay, and since our reference category was 0 and that stood for females and gender, we're going to use that first, and we got to click change. Make very, very important that you click that. Make sure you see that first up there, and then you're going to hit continue. And next we're going to go ahead and go into the save button, and we should probably have probabilities, group membership, cooks. Again, cooks is like the Mahalanobis. It's going to tell you if you have any outliers in any of your data sets, and we want the standardized residuals. Click continue. Let's look at our options. Okay, we want the classification plots, the Hosmer-Lemeshow, goodness of fit. We're not going to mess with residuals here now, but some of the readings say that you should look at the residuals after you run the test, but we're going to put that off for later. And in the correlation of estimates, the iteration history and the confidence interval. Click continue. Click OK. All right, first box has the sample size, 70 total. Number of missing cases, there are none. The second box, the dependent variable encoding, that tells us which number, the 0 or the 1, represents a positive outcome for us. So what we're basically saying is 1 means that they're married, 0 means they are not married. So going down to the categorical variable codings, this is our dummy coding, okay? So remember, we used females were the reference category. We marked them with a 0, and males we marked with a 1. So remember, the output of this data is going to be compared to the females because they're the reference categories, okay? So remember that. So let's get to the block 0. So this is block 0. This is the computer putting together a logistic regression model with no predictor variables. In other words, it's simply looking at the constants. We look at the iteration history box, and we'll notice the -2 log likelihood. This is kind of like a model fit number. But again, we really don't care about this because it has no predictor variables in it. We're going to compare this box from block 0 to the next box coming up is block 1, and the computer will add the predictors by order of strength because remember, we're doing a stepwise here. Okay, so we got a 96.124. So now we're going to go down to the classification table. And don't overly worry about this one either. Again, it's not including any of the predictor variables. What this did was basically says that if you picked anybody at random from your 70 people, you have a 55.7% chance that they will be married. And all it did was it took the married number, 39, and divided it by the total number, which was 70. Okay, so, and then we don't look at that because there are no variables in the equation. And variables not in the equation, we look at this last number here. This is a chi-squared test statistic, and this is the p-value. What it's testing is that the coefficients of the predictor variables in the multiple regression linear equation are not zero. So what this says is that the equation, the coefficients in the equation are not zero. Okay, so let's jump down to block 1. So at the block 1 method, this is the computer making a new multiple regression model, including the predictor variables. So you'll look at the -2 log likelihood. If the prediction variables are actually good at predicting, this number should go down, and it did. If you remember from from block 0, this was like 96 something, okay? So it did, adding the variables did improve the accuracy percentage of the model. And again, the chi-squared test, this number is the result from block O, -2 likelihood, minus block 1, -2 likelihood. And that's what the number is. And again, it's a chi-squared test statistic. Again, so what this says is that the new model is significantly different than the older model. So that means your predicting power just increased. And we're going to look at the model summary. So the Cox-Snell and the Nagelkerke R-squared are what we call pseudo R-squared. But I want you to think of them as effect size. So in other words, what percent of the variance of the accuracy can you explain with this model? And we tend to use the Nagelkerke because it gives you a bigger number. Okay, so this one tells us if the model is a better model or not. But be careful here. Your chi-squared has to be insignificant. In other words, the sig value cannot be less than 0.05, and ours is not. I don't know why there's not a number there, but we're going to go ahead and consider our model to be a significant model. All right, we're going to kind of skip that one. It's for the Hosmer-Lumshaw test anyway. This is an important box, the classification table. You'll notice this reports how many it accurately predicted. So you'll notice from the first block, it was like 55.7% accurate. The second block, it's 80% accurate. So that means once we added the predictor variables, our accuracy of correct predictions went up a lot. It went up about 23%. All right, this is probably the most important box in this entire output here. So remember, we ran a stepwise regression, and the computer picked gender as the strongest predictor. Right? It's significant. And you'll notice this X parentheses B, 15.82. This is a very, very important statistic number. What it means is this, that men are about 15.8 times more likely to be married than women. That's what that means again, okay? Because our reference category is women. This means that men are about 16 times more likely to be married than women. And I'm going to show you a little quick math thing that kind of goes through the exact same thing here, but we'll do that here in a minute or two. So here's a mathematical way to go ahead and calculate the expected B without using the SPSS program. So the expected B literally is the proportionate change in the odds. Proportionate change in the odds. So we take how many females and how many males were in the study. And then we count how many were married in the study, right? 6 out of 29, 33 out of 41. And we turn that into a percent. So 6 divided by 29 is this, 33 divided by 41 is that. So it's roughly 20% chance females are married and 80% chance their males are married. And we calculate the rest of who are not married. So this is the percent of females not married, percent of males not married. So we make an odds ratio. So it's the odds ratio is married versus not married, right? Married over not married, that's an odds ratio for married female. Once you divide those, you get that number, We're going to do the same thing for men. This is the probability that they will be married, probability that they won't be married. You divide that, you get this number. Okay, so there's the odds ratio of a married male. Now we're going to calculate the expected B. And in regular English, it means the odds of one gender being married compared to the other gender. So remember, we set our reference category to be females. So we chose women as the reference, so we're going to compare men to women, not women to men. Just remember that. It can be confusing in the outcomes. So let's calculate our expected B. Here's our odds ratio of married females and married males. We simply divide the two, and we get practically the same number. SPSS will be a little bit different because it rounds at a much different number than we do. So what that means in English, again, is that men are almost 16 times more likely to be married than women. That's all that means. Okay, now let's get back to the SPSS output. Okay, you'll notice that the other variable is not in the model, like age. There should be a second model if it was found to be significant with the stepwise regression model. So let's scroll down a little bit. But look, SPSS decided not to use age because it was not considered a significant predictor. I'll say that again. Age was dropped by the stepwise process because it was not considered significant, and there was no significant interaction between age and gender too. So it dropped both of those. So there will be no more models. So to wrap it up in a nutshell, we're done. So what we did was we made a model that's 80% accurate that will basically say that men are about 16 times more likely to be married than women in this logistic regression. And that wraps up logistic regression, folks. We hope you liked it. MGZ out.
Go pilot, go pilot, go pilot.
That's all, folks. Goodbye.